All right, hello physicists. This is our review for the first week of class. We're going to talk our way through some questions to help us review for the weekly quiz and try to introduce the idea of electric fields. So this week we talked a lot about charging by conduction, where you touch two objects together, some of the charge gets transferred from one to the other. And also charging by induction where you're bringing one object close to a charged object, and that induces a charge within that object. So this you can in a conductor cause a net charge. I would also say it's okay to call it induced charge in an insulator if you bring something close and that has a that's not overall charge, but can have some surface charge as a result of the atoms and molecules getting pulled on by the electric forces by the nearby charge. I would say that's also okay. Today in class, I brought a Van de Graaff generator in. A Van de Graaff generator has a nice positive charge. On top, the way that it gets it is by stripping the electrons off of a silk ribbon that's going around and around and around, and the top also gets the electrons stripped off, and so you get a big positive electric charge on the globe on the top, and you can make nice sparks that way, and we had some fun with that. Now here's a quiz question that is a little bit going to help us think our way through this charging process. So it says we have three identical conducting spheres on individually insulating stands are initially electrically neutral. The three spheres are arranged so that they are in line and touching as shown. A negatively charged conducting rod is brought into contact with sphere A. Subsequently, someone takes sphere C away. Then someone takes sphere B away. Finally, the rod is taken away. What is the sign of the final charge, if any, of these three spheres? Well, it's a little tricky because we did talk about cases where you have one charged object and you take another away, and you can get induced charge. In this case, though, what you have is you have minus, minus, minus. You've got your A, B, and C. And so what I would expect is that at the beginning you would have something like this, where most of the positive charges are going to be collected over here. C is going to end up having a minus charge. So we remove this one. Now this has a plus, and what's ultimately going to happen here is that I'm going to end up getting some sort of a minus charge on B then, because you're still going to have electrons that want to run away from the minus charge here. Like repels like. And then you take away your B, so now we have B and C with a negative charge. But at this point, you might say, okay, well then I'm going to get a plus on this. But no, we are touching this, so my A is also going to get a negative charge by conduction. So in the end, the correct answer for this one on a quiz would be E. A little tricky to think your way through some of these. So what else did we learn? We learned that charge is quantized and conserved. We're getting a charge on objects 1 electron at a time, so 1.602 10 to the minus 19th coulombs is the smallest amount of charge. You cannot have, for instance, 10 to the minus 21 coulombs. you need to have at least 10 to this electron charge coming on and off. We also said that like charges repel, opposite charges attract. They're attracting and repelling via Coulomb's law for static charges. Something to keep in mind is that the amount of force on two objects, for instance, if I had a 5 microcoulombs over here and I had 4 microcoulombs over there, F1 and F2 would still be the same even though the charges are different. Okay, so that's a Newton's third law type of rule where you have same amount of different charges but the same amount of force, just the same way that in gravity you could have a mass and another mass, different amount of mass in each object but the same amount of force acting in equal and opposite directions. So here's another nice quiz question. It says if you have 2 objects, A with charge Q and B with charge 4Q, and they're separated by some distance R, the magnitude of the force on the second object by the first is F. Okay, well they're both positive charges, so the force is going to be repelling them away. So there's my force F. So that's your first situation. Now in your second situation, if the first object is moved to a distance of 2r from the second object, okay, so now instead of having q and 2, that 4q at a distance of r, it's going to be at a distance of 2r. Okay, so there's your new f, still repulsive. If the first object, okay, what is the magnitude of the electric force on the second object? Okay, now remember, the force between these 2 objects, if they're a distance r apart, is going to be given by Coulomb's law, 1 over 4 pi epsilon naught. This whole number is that 9 times 10 to the 9th newtons times meters squared over coulombs squared. And then up here I'm going to have q times 4q, so that's going to give me 4q squared on the top, and my distance between the 2 is r squared. On the other hand, for this f prime, this new force, if I double the distance, let's see what happens with my Coulomb's law. 4 pi epsilon naught, it would give me 4q squared because the charges didn't change. What does change is that instead of putting an r in, I'm going to put in 2r squared. So my f prime then, this is going to have a 2 squared in the bottom, is going to be 1/4 of that original f. Okay, so you have f over 4, and that's our answer. So in this story, we learned that the complication arises because the electrical force is some like vectors. So we always have to have in the back of our minds, oh, we're going to have to be doing vector decomposition, adding the x parts, adding the y parts. And we also have the complication that, you know, the pluses and pluses are pushing each other apart, minuses and minuses are pushing each other apart, pluses and minuses are pulling each other together. Now, an idea that is important for us to come to grips with is the idea of equilibrium. And that's the idea that sometimes, even though lots of individual forces may be acting on a particle, the total force is 0. And when the total force acting on a particle is 0, we say that that particle is in equilibrium. Now, last time in the last video, I went over this problem, and we didn't have time to get to this one in class last time, so so I did this one in class, but I encourage you to go look at the previous video if you would like to see this example. Here's an example from that's more quiz-like that requires a little bit of thinking. So let's do it. It says a charged particle labeled A is located at the midpoint between 2 other charged particles labeled B and C as shown. The sign on of the charges on all 3 particles is the same. When particle A is released, it starts drifting towards C. What can be determined from this behavior? So then it has lots of examples. Is the charge from A bigger than the charge on B? A bigger than C? C bigger than A? B bigger than A? B bigger than C? Okay, well, it says that the sign on the charges of all three is the same, so that's helpful. And what does that tell us? Well, it tells us that A is being pushed away from C, and it's being pushed away from B. So the force from B is pushing this way, because the A and B have the same type of sign of charge. And it's also A is being pushed away from C. However, the fact that the object is drifting towards the left tells me that this FB is greater than FC. So, because I know the form of the it's going to be QB QA. That's going to, the force of B is going to be related to the product of those two from Coulomb's law, and FC is going to be proportional to the QC times QA. Okay, the fact that the force on B from B pushing to the left is bigger than the force of C pushing to the right tells me that the charge of B, the magnitude of the charge of B is bigger than the magnitude of the charge of C. Okay, because QA is going to be the same for both of these, so QB is larger than the charge on C. All right. In our last video, I also went through this problem, but remember the idea here is that, for instance, in this particle on the left, if two charged balls are hanging and you have the force of gravity pulling this way, the electrical force pushing out, and the tension force pulling this way, you can go ahead and set up equilibrium conditions where the sum of the tension force in the x direction counteracts the force of the electrical force from Coulomb's law, and the tension force in the y direction counteracts the force of gravity. And by doing that, you can solve and you can find a relationship between x, the difference between the pith balls, and the charge. So there's your q on each ball. We're assuming each ball has a charge of q and a mass of m, and then epsilon naught is a constant. G is your 9.8 newtons per kilogram here on Earth, and so yeah, if you're looking for where that is in the previous video. Now, the idea that gravitational forces and electrical forces are both communicated by fields is one that I've already talked a little bit about, but I just want to remind you, forces are in newtons, and so the idea of a gravitational field is that if you put an object that has mass m in that field, the amount of force that it's going to experience depends on the gravitational field strength at that position. So the mass has units of kilograms, and this g must have units of newtons over kilograms. The kilograms will cancel out, and you'll get newtons on both sides. Okay, and remember, newtons over kilograms is the same as meters per second squared. So we could be a little bit sloppy, and g was also the gravitational acceleration. We can't be sloppy like that with using SI units for charge, because in this case, our idea is that you have some sort of an electric field for charge. The direction that it points is the direction that a positive charge would get pulled. And again, we have a force in newtons pulls on a charge, charges in coulombs, and the units on our electric field therefore must be newtons per coulomb. Okay, so if you put a charge, the direction of the electric field tells you the direction that the force is applied, and then the amount of force is given by taking the product of the magnitude of the amount of charge and the magnitude of the field strength. Now here's a nice simple example to think about. It says, suppose that right here we have a constant electric field between these two plates of 4 newtons per coulomb. Okay, so it's pointing in a particular direction. It's pointing in the, I'm thinking about this as an x direction, an I hat direction. So E is the vector pointing from one side to the other in this example. Now, let's just ask a question. What if we put a little ink droplet that has some charge on it? It's going to get pulled from one side to the other. It's going to get accelerated, rather, by this force. What kind of force and what direction would be acting on a droplet with a 5 microcoulomb? So if I have Q equals plus 5 microcoulomb, the force is going to be in the direction of the electric field, and the amount of force is going to be just 5 microcoulombs times 4 newtons per coulomb. So that would give me 25 times 4 is 20 microcoulombs in that I hat direction. Now the reason that I point that out, so there's the force, is that what if I had instead a Q that had a minus 5 microcoulombs? Well, what would happen is that it would get pulled in the opposite direction. You see that the way that we're making this electric field is with a bunch of plus charges over on this plate, a bunch of minus charges on that plate. This minus charge is going to get repelled by the other minuses and pulled towards the pluses. Okay, so my force is going to be in the opposite direction, and it's going to still have a size of 5 microcoulombs times 4 newtons per coulomb, but it's going to be in the opposite direction. Minus 20 this should be not coulombs, micronewtons, newtons times I. Okay, so this is pulled in the plus I, the plus x direction. This is pulled in the minus I, the minus x direction. And so that's one of the complications that we're going to have to deal with in when we think about electric fields. Now, electric fields give us a new way to think about Coulomb's law, and we're going to do more of this in our next video. Each charge contributes a vector contribution to the electric field, which pushes or pulls on a charge at a particular position. Now, something just to notice here is that if we have our F equals K Q1 Q2 over R squared, that's our Coulomb's law, and we also have our F equals Q times E. So let's think of our Q1 times E. We could specify which one. If we want to think about our Coulomb's law in terms of electric fields, we could just set these two equal to each other. And in that case, we would have Q1 times E equals K Q1 Q2 over R squared. And we could divide each side by Q1. In that case, the electric field contribution from Q2 would have a magnitude of K Q2 over R squared. So what we're going to learn how to do on Monday in our next video is going to be essentially this. This is going to have to be a vector. If you have a positive charge, the electric field contribution points out because it would push away another positive charge. If you have a negative charge, the electric field contribution would point in because that would be the sort of contribution that would pull pull a positive charge in. So if you are wanting to build some intuition up with these, I recommend taking a look at this PhysicsFET on charges and fields. And what this shows us is, let's say that we put a positive charge out there. This is a way to visualize the electric field. The little pointers are telling us what direction the electric field is pointing in, and how bright they are tells us how strong. So the electric field would be stronger closer to the charge, weaker farther out. If we take an a positive charge and a negative charge, this is called a dipole configuration, where I have the electric field that's pointing out from the plus and in towards the minus. If I put another plus charge in here, it would essentially be pushed on in the direction of these field lines. You can imagine connecting up these, so we'll talk about doing that. On the other hand, if I had two positive charges, it would look quite different, because the field configuration would be pushed away from each one of these. You'll notice there's a line in the middle where essentially the electric field is pointing out like this, and so that essentially the forces of these in one direction cancel out. They cancel out in the x direction along this line. So I think it's fun to take a look at these. You can also, if you want, you can go ahead and make like a quadrupole pattern. This is a little interesting. And so you can see all sorts of interesting patterns that can be made with charges. And there's been a lot of work done on this sort of material if you want to take a more advanced course in electromagnetics. Okay, but that's enough for today. So what did we do today? We said that forces continue to sum like vectors. Where we're going to go next is that instead of thinking about the force on an object as or a charged object as being due to the individual sums of all of these forces, instead we think all of those different charges contribute to the electric field, which is a single thing at a particular position, and the electric field then, when you put a charge at that position, pulls on the charge, making an electric force. And so that seems like what did we get out of that? Well, nothing so far, but we're going to develop this idea a lot, and we're going to think about a lot of different sources of electric field, from lines of charge to disks of charge, and then eventually next unit things like batteries. And then the force on the electrical field on the electrical charges is the product of the magnitude of the charge and the magnitude of the field strength. Okay, so that's enough for today. We'll see you next week, and thank you for watching.